Year 13 revision, short revision video number 26. So it's clear we have a mechanics question here, and we're given some information at the start. Rory runs a distance of 45 metres in 12.5 seconds. He starts from rest and accelerates to a speed of 4 metres per second. He runs the remaining distance at 4 metres per second. So he accelerates from rest to a speed of 4 metres per second and then travels at this constant speed. So the first model that we are proposing is one in which the acceleration is constant until time t seconds. So we need to, for part one, sketch the velocity time graph for Rory's run using this model. So part one, let's set up some axes for our velocity time graph. All the motion is taking place in the same direction, so we can ignore a negative velocity axis. So 0, there's the velocity, meters per second, and then there's the time in seconds. So we know that we start with a 0 velocity, so we start from rest, and we're assuming the acceleration is constant, so the first part of the graph will be a straight line graph indicating constant acceleration, like so. And we know that this allows Rory to reach a speed of 4 metres per second. Now, we know that the acceleration remains constant for a time t seconds, like so. And after this time, he travels at a constant speed of 4 metres per second, so we want a horizontal line, and the whole journey takes a time of 12.5 seconds. There is our velocity time graph. And we've now got to calculate the value of t. So what other information do we know that we haven't yet used? The total distance travelled is 45 metres, so we know that this area under the graph, the area of this trapezium, is 45 metres. So we can set up a quick equation. Half, now the parallel sides are 12.5 on the base, and then this measurement here, which is 12.5 take away t. So this gives me the sum of the parallel sides multiplied by the distance between them, which is 4, or the height of the trapezium, and that must equal 45. And we can then simplify and solve this equation to work out the value of t. And t comes to a value of 2.5 seconds. Part 3. Find an expression for Rory's displacement at time t seconds for a time that's between 0 and t. So what we're saying here is, let's imagine that Rory has travelled for a time t seconds there, and that's a time that's between 0 and capital T, and we want to find an expression for the displacement, which means we want to find an expression for this area, or we could use a constant acceleration equation to work this out. So how are we going to do this? Well, first of all, it would be useful to actually work out the acceleration. So I'm going to start off by calculating the acceleration, which is very easy to do because remember, acceleration is the gradient of your velocity time graph. And in this section here, we can calculate the acceleration very easily by doing 4 divided by the value of t, which is 2.5, which gives us a constant acceleration of 1.6 metres per second squared. If I then set up my SUVAT information, S is equal to the displacement that we're actually trying to find out. So that's what we want to do. We want to find an expression for the displacement. U is equal to 0. V, we don't know. A is equal to 1.6, and t, we're trying to find an expression for the displacement at time t seconds, so we do need that. So I'm going to cross out v because that's the information that we're not interested in. And then we can use s equals ut plus a half at squared, a constant acceleration equation. Substituting in, ut will be 0, so we then have a half times 1.6 times t squared, which is 0.8 t squared. So our expression for the displacement at time t seconds during the period of constant acceleration is s equals 0.8 t squared. We could also have done this by finding the area of the purple shaded region in the graph, but that might be a slightly trickier way forward compared to using the Suvat equation. So, part 4, use this model to find the time taken for Rory to run the first 4 metres. Okay, so what I'd like to be careful of is the area of this region here, which I'll just highlight in yellow, and we can work out that area very easily. It's a rectangle which has a height of 4 and a base of 10, because of course we know t is equal to 2.5. So that's equal to 40 metres, which means that the area of this triangular region, which I'm going to shade all in blue, that's obviously 5 metres. So that's clear that the 4 metre mark must fall within that phase of constant acceleration. So it's absolutely fine in part 4 for us to set s equal to 4 metres in this formula here, and to work out what the value of t is from there. So we get t is equal to the square root of 5 seconds, which we can obviously evaluate and then round sensibly. So that's 2.236 or 2.24 seconds to 3 significant figures. But it was important to check that the 4 metre distance occurred within the phase of constant acceleration, because if it encroached the phase of constant velocity, i.e. fell within the rectangular part of the trapezium, the yellow shaded area, we would have to look at the 2 parts of the distance separately in order to work that out carefully. So, the next part of this question, Rory proposes a refined model in which the velocity during the acceleration phase is a quadratic function of t. The graph of Rory's quadratic goes through 0, 0 and has a maximum point at s4. In this model, the acceleration phase lasts until time s seconds, after which the velocity is constant. So, sketch a velocity time graph that represents Rory's run using this refined model. So, let's sketch another velocity time graph. Set up our axes as we've done previously. Okay, so we know that the graph goes through 0, 0. And has a maximum point at s4. So the acceleration phase lasts until time s seconds, after which the velocity is constant. So let's say that this is s and this is 4. Then what we're saying is the graph has a quadratic shape, so it must be curved. And then at that point there, we have a constant velocity, so the graph levels off and is horizontal after time t equals s. Okay, there we go. Now the last part of this is quite interesting. State with a reason whether s is greater than t or less than t. Now, let's imagine s and t were equal to each other. If I then superimpose the graph that we drew in part 1 on top of the graph from part 5, well, the first part of the original graph was a straight line like that, which means that the area would be less in the first scenario than in this new quadratic scenario. So if s is equal to t, then areas are not equal. Now, if t were to the further right of s, so t were greater than s, you can see that if you then drew in the graph for the first scenario, then you'd end up with the red region still being larger than the region for the first scenario. So the only way that you can get the two areas to be the same is if s is less than t.